Okay. Uh-oh, tablet's not on. One sec, guys. So, all right, transformations again. Last time we're going to talk about transformations in a formal context. I will just bring them up regularly otherwise. Um, so in your book, primarily they're going to work with y equals log x. So if you guys ever see log x with no base explicitly written, it's assumed that the base is 10. Okay, and again, you've seen this doing pH. You always are trying to solve like 10 to the power of whatever. So the base is 10 if there's nothing there. On your calculator, you're going to have two buttons. One of them is, uh-oh, okay, so you'll have a button that's like this somehow, okay? And then you'll also have a button that is just log or log x. One of them assumes a base of 10. Okay, so this one is going to be base 10. This one you can insert a base. Okay, so the book sort of rolls with the idea that you're going to use the base of 10 as your parent function. The issue with that is that it is really hard to work with. Like if you start applying stretches and compressions to something that's increasing by the order of 10, your graph gets really unmanageable very quickly. So when it's exponential, it becomes very steep, right? And like leaves your grid. For the logarithmic function, the increase isn't so bad past the x-axis or past that x-intercept. It's just that the points that are close to the y-axis very, very quickly become like 1 over 10, 1 over 100. So it's hard to draw, I guess, is the moral of the story when you're working with a base of 10, okay? For test purposes, if I'm asking you to draw something using transformations, I will probably use a base of 2 or 3, just so that you have numbers that you can work with that are more manageable. Other than that, transformations are exactly the same as they have been all year. So you know that the absolute value of A, sorry, I should put something here. Base of 10 creates ugly numbers quickly. Okay, right? Because even like 10 squared, oh, it's 100. So they're just big. It's not good. Okay. Um, okay, so then again, your transformations are the same as they have been for 2 years. The absolute value of A is the vertical stretch, and then if you've got a negative sign there, you've reflected over the x-axis. Your horizontal stretch is 1 over k, and then if k has a negative in front of it, you reflect over y, and then d moves it side to side and c moves up and down. Don't forget to common factor k. So there's some of you where I've been writing that on everything all year long, and probably Miss Richardson was last year too. Make sure that you common factor k out before you start trying to apply transformations, okay? Your domain for your transformed function is usually going to be x is greater than d, because d is your horizontal shift, so your vertical asymptote will shift horizontally, unless your function has been reflected. If it's been reflected, then it's going to be x is less than d. Your range is always all real numbers. Okay. And there's one practice problem, and hopefully you guys remember how to do transformations, and this day was not too bad. So again, starting from the graph that we used at the beginning of yesterday's note, so the log of x with a base of 2, we're going to use that and transform it, okay? I'm never going to change the base in a transformation. It's just going to be transformations as you know. So again, don't forget to common factor. 2 log, oh no, hate when that happens. 2 and then common factor. So when you divide by 0.5, 1 divided by 1/2, if you take a whole thing and split it into 2 halves, it becomes a 2. Okay, so make sure you common factor properly. Divide, don't multiply. So this means that the formulas that I'm using, or you're doing it the way that a lot of you do with your transformation tables, I don't care. But for each point, we are taking them and we would be doing, I'm just going to put it up here. So x over 0.5 or 2x, okay, minus 2, and then 2y plus 1, okay? So I'm just going to take my x, multiply it by 2, and then subtract 2. So a quarter times 2 is a half, minus 2, negative 1 and 1/2. And then negative 2 times 2 is negative 4, plus 1 is negative 3, and so on and so forth. So a half times 2 is 1, minus 2 is negative 1. Negative 1 times 2 is negative 2, plus 1 is negative 1. Uh-oh. Seriously, though. Okay. 2 minus 2 is 0. And then 0 plus 1 is 1. And 8. Once it starts doing this, I'm pretty much done for. 2 times 2 is 4, minus 2 is 2. 2 times 1 is 2, plus 1 is 3. And 4 times 2 is 8, minus 2 is 6. Oh, come on. There. 4 plus 1 is 5. All right. So that should be correct. And now I'll actually put some axes on there and draw it, which is going to be painful for you guys to watch. So just do your own. And then double check with mine and make sure that they match. And I got the table of values. I guess I should tell you guys that by just flipping the points on y equals 2 to the x. So that was where those came from. That's not something new to learn. Just take the inverse of the table you already know. Okay, so there is my original function in its poorly drawn state. And then I'll use a different color and do my transformed function. Okay, and then just make sure that you remember that you have a vertical asymptote at -2 here. So don't cross it. Do your best to be better than me when you draw that, and that's your transformed function. Okay, and then if you had to state the domain, it just has to be greater than -2, and then your range would be all real numbers.